Yes, so it's time for the third lecture in this course, and this part consists of two pieces. The first one is just some simple combinatorics that you will need going through the main feature today, which is distributions. The reason I'm going through combinatorics also is because some of you might not have all the bits and pieces that you need in order to understand distributions. So I will go through a few basic things about combinatorics first, and then I'll go on with distributions. Talking about combinatorics, we need some basic combinatorics. So it's basically about in how many ways different things can be done. For instance, we have 10 students to choose from. We want to form a group of 3. In how many ways can this be done? The question is not complete yet, because we also need to know, do we care about the order that we choose the people in? For example, do we need like a chairman, a secretary, and a head of economics? Or is it just a group of 3? For instance, if we have 10 students and we want to send away 3 students on some kind of trip to somewhere. We'll start from the beginning. So the multiplication principle, version 1, an operation performed in k steps where each step can be done in n1, n2, etc. up to nk different ways. Independent, that's really important, independent of each other, can as a whole be performed in n1 times n2, etc. different ways. And yeah, you probably remember this from secondary school. So okay, first if you're supposed to choose something, first you choose it in 3 ways and then you choose in 5 ways. So the number of choices will then of course be 3 times 5. Another example, sorry for the Swedish spelling anyway. So how many Swedish car signs can we make allowing all normal possibilities? With normal I mean we have, in Sweden at least, we have 28 characters to choose from and 10 numbers. If we then say, okay, that one and that one and that one can all be chosen in 28 different ways, and these can be chosen in 10 different ways. Hence, I just multiply everything together, and this is the amount of results I can get. That's the basic thing. Then we'll get into something called permutations, or also called ordered selections. So with the permutation of a finite set, we mean an order of the elements. So simply a way of putting the elements in a row caring about the order. So for instance, let's say we have the numbers 1, 2, 3, and we want to put them in a line somehow, count them, 1, 2, 3, 2, 1, 3, etc., etc. You can do that in 6 different ways, like this. That means 3 times 2 times 1. And why is that? Well, because when you choose what you want to have in the first place, you have 3 different things to choose from. For every such choice, you can pick the next one in 2 ways and the next one in 1 way. And that is calculated as 3 times 2 times 1, also denoted by 3 factorial. Given a set M with n elements where n is greater than 1, the number of possible permutations of the complete set is n factorial. A bit more formal then. The number of ways of ordering k elements chosen among a totality of n is this. Why is that? Well, when you choose the first element, you have n ways to choose. And the second, well, you've taken 1 away, so n minus 1, etc. If you remember, if you have 10 students and you're supposed to pick, say, 3, the first one, you can pick the first one in 10 ways, the second one in 9 ways, and the third one in 8 ways. So how does that figure together with this formula? Well, that is, in fact, exactly 10 factorial divided with 7 factorial. Exactly as this formula stipulates. Also note that if we want to pick one element from n, that can only be made in n ways. If we want to pick one more than k, by going through this really cumbersome process, we end up with the number of ways you can pick k elements times n minus k. You probably won't use this that many times. We have a kind of a special thing here. So let's say we have 9 letters and we want to create words using all those 9 letters. But there's a specific problem here. Some of them are the same, called permutations of multisets. Well, first we think about all the letters as different. So this gives us, of course, then 9 factorial possibilities. But some letters are the same. So for instance, we have 4 of the letter U. Thinking about the words that can be created this way, we realize that lots of them will be the same. The only thing that will differ would be the order between the different U's. So you could, for instance, set tags on the U's like U1, U2, U3, U4. But in the end, when you create these words, you realize that regardless of the order between the U's, it will still be the same word. In how many ways can they then be reorganized? Well, obviously, because there's 4 of them, it's 4 factorial. A way of then kind of taking away the order, we could just divide with 4 factorial, because we have right now 4 factorial times as many words as we want. So let's just divide with 4 factorial. And then we have to do the same thing concerning the G's and the D's. So that means in the end, what we actually have is 9 factorial if we treat them all the letters as different. But if we want to kind of take away the order between the U's, we have to divide with 4 factorial. When it comes to the G's, it's 3 factorial. And the D's is 2 factorial. So in the end, what we have left is quite a bit less. So only 1,260 different words. This gives us a general formula for permutating multisets. So if I have in total n, but I have k1 of one character, k2 of another character or object, and so on. If I want to know the number of permutations of this multiset, I can use this formula, which is easiest remembered by using this small example. And now for something that we will use in the distribution part. So unordered selections. If we don't need to know the order between the items, the only thing we're interested in is in what items have we chosen. So pick a subgroup of 3 among 10 given persons. So we can pick those 3 in 10 times 9 times 8 different ways, counting if we count the order. Okay, that's permutations as before. But to take away the order of these, because obviously if you have like A, B, C, and B, A, C, or I don't know, C, B, A, they are all the same. And in how many ways can you reorder 3 items? Well, 3 factorial. We need to divide with 3 factorial. So this is what we get then. And if you think about it, you could have done this a bit different. Instead, say you write 10 factorial and you divide with 10 minus 3 factorial, which if you think about it is 7 factorial. So this is kind of like the tail. If you have 10 factorial, you will have 10 times 9 times 8 times 7, etc. And this will be the tail, 7 times 6, etc. So by dividing with this piece together gets to be just 10 times 9 times 8. And then you divide with 3 factorial. So this is the number of unordered groups of 3 among 10. A bit more formal, it looks like this. So if you want to pick k elements from a set of n, you get this. N choose k. And this is exactly the formula that we had on the last page. We say n choose k. And we will be using this. And it's called a binomial number because of some math that I won't be going through now. It has to do with the binomial distribution, amongst other things. And you should note that to pick 2 among 10 is the same as to pick 8 among 10. Why? Well, because when you pick 2 out of 10, what you actually do is you're dividing this pile of 10 into 2 piles. And if you pick out 2 or pick out 8, which is the rest, doesn't matter. You're basically dividing these 10 into 2 piles. One that you want to have and one that you don't want to have. 10 choose 2 and 10 choose 8 will give you the same result. To pick all elements or to pick none of the elements can only be done in one way, of course. Okay, so that was some basic things about combinatorics, and hopefully you've done that before. Otherwise, I would recommend that you look back in some old school books and go through a few exercises, because you do need to understand how to use at least combinations, so unordered selections. But now, let's hit this instead. So, discrete distributions. We have talked about random variables. We'll first focus on discrete random variables. Variables that can only take on discrete values, separate values, not continuous, but discrete. So we have a motherboard, for instance, with 3 contacts. We want to observe the number of defect contacts after a certain time. So let's say that we define the random variable x as the number of defect contacts. And of course, the sample space then would be 0, 1, 2, 3, discrete values. By experience, we know that the probability for having no defect contacts is 0.65, and for 1 is 0.2, etc. Okay? This gives us a probability distribution that will be looking like this. So the probability for 0 is 0.65, for 1 is 0.2, etc. Really important to note is when you add all of these probabilities, they have to add up to 1, obviously, because 1 is, if the probability is 1, that's the complete thing. That's the sure event or definite event that will always be. Most often, a probability distribution can be expressed by a mathematical function in some way. And this function, p of x or f of x, will be called the probability mass function. And we know that if we add all the probabilities for all possible x's, I need to have 1. Just as we had on this page. If we add all of these together, we will have 1. And associated with the mass function is the cumulative distribution function. And what is that? Well, of course it's related, but what it actually means is you will add all the probabilities up to a certain value. So the cumulative distribution function for instance, 1, in the case on the last page, would be if you add these two together. So what is the probability that you will have a result being 1 or less? Of course, 0.85. If we think about the probability for x being greater than a certain value, can of course get that by taking 1 minus x being less than or equal to a certain value, which is then of course 1 minus the cumulative distribution function in this case. To me, the easiest way to remember all of this is just to look at one of these simple examples. What's the probability that x will be 1 or less? Well, as I said, just add these. What's the probability that the result will be greater than 2? Well, the easiest way would be to say, okay, greater than 2, take away all of this, and the rest will be that, of course, if you want to use this cumulative function. Let's look at one example. In the example from before, with the gas igniting and exploding, we add the variable y for the number of injured. We say that if we don't have any ignition, we won't have any injuries. If we have an ignition but not an explosion, we will have 1 injury. And in this case, where we have both an ignition and an explosion, we'll have 2 injuries. And we have these values from before. The probability for y equals 0 is the probability for the complement of a, which is, using this, 0.995. The probability for y being 1 is, of course, the probability of a times the probability of not b if we know that a has happened. This is just going back to the conditional probability. And in that case, that would be 0.0045. And in this case, we have if y equals 2, which means this happens and this happens. What's the probability for A times the probability for B if we know that A has happened? And we have that one too. And if we calculate that, we get 0.0005. Putting all of this together, we get a probability mass function for y. Because we have now calculated the probability for the possible outcomes. So 0, 1, 2. And these are the results. And also, of course, if we add these three together, the result must be 1, and it is. A slightly more complicated, but still quite understandable example. In a process of 2 steps, we sometime must return to step 1 after step 2. So you start here, you go on to step 1, you go on to step 2, and sometimes you have to return for some reason. Something might have gone wrong, so you have to go back with a probability of 0.2. Okay, so I've tried to express this using this table. So you can start, you will go to 1, to 2, and stop. And the probability is, well, the first 2 steps are sure steps. You have to do them. The last step will happen with a probability of 0.8, going from here to here. I mean, going down is 0.2, so it has to be 0.8 going there. If we say instead that we have 5 steps, going like start, 1, 2, going back to 1, and then 2, and then stop. So we have 1, 1, of course, the first 2 steps, then 0.2, going back, and then we have to 1, then we have the certain event going to 2, and once again 0.8 to come to stop. And so on. Because this will just go on and on and on and on, and you will get 0.2 to the power of 2 in this case, to the power of 1 in this case, to the power of 0 in this case. So could we describe this somehow? Well, might take a while to think about this, but if we define x as the number of steps in the process, we can define the probability mass function as this. If we enter 3, that means we will have 0 up here. 5, we will have 2 divided by 2, so 1. So that's this case. 7, we will have this case, and so on. So this is actually then some kind of probability mass function for this process. A bit strange, you might feel, but still it works. We will now go on looking at a few distributions that are especially important and useful. So we'll start with something called the binomial distribution, and this is when you kind of need what we talked about when we talked about combinatorics. So an experiment is performed n times. All experiments are independent of each other. So it can be like flipping a coin or something like that. The result can either be a success with a probability of p or fail with a probability of 1 minus p. So we have this binomial thing, kind of fail, succeed. So you have 2 possible versions, and one is fail, one is success. And we know that p is the probability to succeed, and 1 minus p will then obviously be the probability to fail. And we want to know how many successes x we get from this. Then the binomial distribution has the probability mass function that will look like this. And why? Why is that? Well, because if you have n, if you do something n times, and you want to know in how many ways can I pick out x successes from n, that is exactly this binomial number that we talked about before. And you have the formula to calculate it. Okay, so that's the number of ways you can do it. But for each and every one of those, what will the probability be for that outcome? Well, thinking back to the start and stop thing, it is the probability to succeed to the power of number of successes times 1 minus p to the power of the number of fails. So this isn't that hard to understand. So this is the number of possible combinations to have, and this is the probability for success in x times and to fail n minus x times. And if we want to say that the variable x has the distribution binomial distribution with n experiments and the probability to succeed in each case is p, this is the way we write it. So x tilde bin np. Okay? And just to remind you, n choose x tells us in how many ways we can succeed x times out of n trials. In connection to this, we state that the cumulative distribution function will be this. And it might look a bit strange, but what you do is, so if you, let's say you flip a coin 10 times and you want to know what is the probability that you will succeed 3 times or less. Well, then you will add the probability to succeed 0 times, 1 time, 2 times, and 3 times. Hence you have this summation of, in that case, 4 different cases. And that is basically what this says. Take the sum from 0 up to the number that we're talking about. And of course, this value will be 0 if x is less than 0, because you can't flip a coin minus 2 times, obviously. If x is greater than the actual number of flips, yeah, well, then the probability will be 1. When we talk about this cumulative distribution function, we're actually talking about what's the probability that the value of the random variable is less than or equal to x. And we will be dealing quite a bit more about with this in the future. So this is not the last thing you've seen of this. An example then, the probability for a break in the production during a random day in a week, where we have 5 days, is supposed to be 0.1. The breaks will happen independently. We create a random variable, being x, number of breaks in a week. So number of days with a break in a week. So we have a variable x that is distributed binomially. We have 5 experiments or 5 happenings, and the probability to succeed, if you can say that in this case, each time is 0.1. So this is what we have. What is then the probability for having breaks exactly 2 out of 5 days? Well, by going by the formula, to pick 2 out of 5, you can do that in this many ways. 5 choose 2. And those 2 that you've picked, we know the probability to have that. So it's 0.1 and it's 2 of them, so to the power of 2. And the other 3, 5 minus 2 is 3, we need to use the probability 1 minus 0.1, 0.9. So when we calculate all of this, we get this value. And this is calculated, well, you remember the formula, I hope. And it can be slightly simplified if you realize that you're supposed to pick 2, so 5 times 4, and take away the order, which is 2 factorial. That's this. 5 times 4 divided by 2, so 10. What is the probability for having breaks at least 1 day? So x is supposed to be greater than or equal to 1. But instead of calculating the probability for having 1 break, 2 break, 3 break, etc., you could say, okay, but if I then instead calculate the probability for having no break and take away that from 1, that's by far much easier. So this is what I'm going to do. Using this formula, but instead of having x equals 2, I will have x equals 0. This is what I get then. And the result will be 0.41. You need to be clever sometimes. So instead of calculating using this formula for x equals 1, 2, 3, 4, 5, you can just take this formula and take it away from 1. So that makes things much easier. Okay, that was the binomial distribution, and definitely we will be back and talk loads more about that. But for now, we need to go on a bit. I don't know if you heard about the Poisson distribution. Just you follow me for a while and I'll try to explain what this is about. Let's look at something quite similar to the binomial distribution. So you know that the binomial distribution works when we have a fixed number of events, like flipping a coin 10 times or 100 times or whatever. And we know that we have a constant probability of success for each and every instance. But imagine that we don't really know the number of trials that will happen. In fact, they will happen quite often. Or you could also say they are happening all the time. We'll be focusing on the only thing we actually know is the average number of successes per time period. So we know like the rate of success per time period, but we don't actually know the number of trials, and we don't know the probability of success that led to the rate. We'll start by defining a number called lambda equals n times p, where if we had known n, this would be that n, and if we had known p, that would have been that. And this, in the end, the lambda is the rate of success per time period. Because if you had known that you had a certain number of experiments during a period and you know what the probability would be to succeed in each of those cases, the rate of success for that time period would have been n times p. So we define that number and we say, okay, it's lambda. So that's the number of trials n times and the chance of success p for each of those trials. Like I say, we don't actually know the number of trials. It could be something like, if you're at the till somewhere in a shop and you want to know how many customers will I have in a certain time. This is definitely a case where this Poisson distribution kicks in. So you can think of it like this. If the chance of success is p and we run n trials per time period, we'll observe n times p successes per time period on average, okay? So that's the kind of the explanation for this, just like I said before. That's then our observed success rate, lambda. There is a mathematical explanation for why it works the way it works when it comes to the actual formula for this, but that one is quite complicated, the process to find it. But this is the formula. So this is the actual formula. And how we find it, it's really complicated, so I won't be doing that here. And also, please note that in this formula, I'm using m instead of lambda. And the reason I'm using both lambda and m is because different books and different articles are using different values. So I kind of wanted you to see that you could either go for lambda or for m. Doesn't matter. It works exactly the same. And this m or lambda is the average success rate. And of course, to get the cumulative distribution function, it works exactly the same. You just add all. So if I want to know what's the probability that x will be less than or equal to 2, I will just add the cases where x equals 0, 1, and 2, and then I'm done. So that's the cumulative distribution function. So this distribution is used when dealing with problems where we focus on the number of successes during a specific time. Like I said, if you're at the till, how many customers will you have, for instance, in an hour? If you know the average rate that you usually have. So then you can calculate, if you know that the average rate is 7, you can then calculate what's the probability that you will have 10 this hour. You would then use this formula. Another example, let's assume that the number of bad accidents per year at a company follows a random variable that is like this. So it's Poisson distributed with this the 2, which is the average of 2 accidents a year. What then is the probability for more than 3 accidents a year? So I want to know what is the probability that x is greater than 3. And I can solve that by saying 1 minus what is the probability that x will be less than or equal to 3, of course, because we're talking discrete values now. So greater than 3, in that case, I will take away 3 and down. And that looks like this. So I'm using the formula we had on the last page. This m, 2 to the power of 0 divided by 0 factorial times e to the power of minus 2. And then going on, the only thing that changes between the case where x equals 0, 1, 2, 3 is just this, that value, that value. So those are the only one that will be changing. And if you just add all these together, this is what you get. We won't be dealing too much with Poisson distribution It's a discrete one, and it's modeling cases where you want to know the number of successes during a certain time period. And as I tried to tell you, it's kind of like a generalization of the binomial distribution. And the mathematical process to get from the binomial distribution into this is quite complicated, so I won't tire you with it. Also, it can be interesting to know that it can be shown that if an experiment is performed n independent times, and the probability that it succeeds each time is very, very, very small, the number of succeeded cases is almost approximately Poisson distributed with then m equals n times p. This is called the law of small numbers, and it's usable if n is greater than 10 and p is less than 0.1. But I would say if n should actually be quite a bit greater than 10 and p should be quite a bit less than 0.1 in order for this to really be something that you could use. Okay, that was discrete distributions, like if you count things and stuff like that. But what about continuous distributions? So things that can take on any kind of value. If you, for instance, if you measure something, if you take the time for something, you can have any kind of result. It's not discrete values, they are continuous. And then we talk not about a probability mass function, but a probability density function. It has the same meaning, basically, in both cases, but they have different names. And you can think about these as some kind of scale histogram. I can have all kinds of results, and if I divide them into small classes with a certain width, and I take the frequency and use that as the height, I could get something like this. You probably recognize this as some kind of normal distribution. And if you were to take these bars very, very thin, you would get something really smooth like this. And if I know this function, a red graph, I can find the probability for x being between two values by calculating the integral, which is basically the area below the curve between two values a and b, if you have forgotten that. And also remember that the demand for this to be a probability density function is, of course, that if you integrate from minus infinity to plus infinity, so that you actually take all possible values, you're actually checking all the area all the way, it should be 1. And this probability density function must of course be greater than or equal to 0 for all x's. Otherwise, I mean, it couldn't be below 0 because we're talking probabilities here. And one more thing that you should remember, because this is the way you define the integral. If you integrate from one value to the same value, what does that mean? Well, it's if you want to get the probability for a specific value. So if we're measuring the length of people and someone asks, so what's the probability that a person will be exactly 1 meter 78 centimeters? The answer is 0. The theoretical answer is 0, because I'm trying to integrate from one value to the same value. And in math, I hope you remember, the integral, when you have the same value starting and stopping, the integral will always be 0. So that's important to remember. But what that actually means, if you're measuring, you will probably be slightly taller than 178 or shorter than 178 if you measure good enough. Also, the idea with greater than or equal and so on, which was really important when we talked about discrete distributions, is not in any way important when we talk continuous distributions, because we can just use these as we want, and that's because the probability for a specific point is always 0. So if you're calculating the probability that x is greater than or less than b, or if it's basically equal on both sides, there's no difference. And that's important to remember. And that's because, like I said, if you look at the probability for a certain point, it's always 0. And the cumulative distribution function then, if you integrate from minus infinity up to the specific value we're talking about, you get the cumulative distribution function. So if I want to know, for instance, what's the probability that the value will be below this point in this curve? Well, I will just integrate from minus infinity up to this point, and then I get down. It's proposed that f of x equals 4 times x to the power of 3 could be a density function when x goes from 0 to 1. This works because if we integrate from 0 to 1, the primitive function for this is x to the power of 4. If you just differentiate this, you will get this. So yes, it works. And then evaluating this first for 1 and take away what happens if we enter 0, we'll get 1. So yeah, that works. And now we can then calculate what is the probability that x will be between 0.4 and 0.8. Well, we'll be using the exact same integral, using the exact same primitive function. So 0.8 to the power 4 minus 0.4 to the power 4, and that will be 0.38. This is not any kind of distribution that we will use, but this is just an example of how it could look. And if you look at this image, you can also see what we've actually done. We've calculated this area, which is 0.38. And what's the probability that x will be greater than 0.62? Thinking about it, when we know that x will always be between 0 and 1, this means that x has to be between 0.62 and 1. So once again, we can use this integral and calculate and get the value. So let's look at some continuous distributions that we'll be using quite a lot. So the first one, which is not used too much, but it is anyway quite important, is the uniform distribution. So it's a distribution where you have the same value, the same probability all over. And that's the reason it's called uniform. Right here, I've chosen a really simple one. I'm going from minus 0.5 to plus 0.5. And we have to make sure that the height is the way that if you take the complete area, it has to be 1. But because of the width, the fact that the width is 1, the height should be 1, because then the area of this will be 1. This is sometimes called the rectangular distribution, and it is denoted by RE of AB, where A and B will be the limits. The lower limit is A, the higher limit is B. And the cumulative distribution function will be this. And I mean, this isn't strange and this isn't strange. This might be a bit odd, but if you think about it, it is not really that strange, because b minus a is the complete stretch and x minus a is the part that we're talking about. So what's the probability that x is less than or equal to 0? If we enter that, we'll get the answer. But like I said, it's not used too much, but here's an example anyway. We're measuring trees and the result will be in whole meters. The error called x, and that's a random variable, and let's just go for this. So we're measuring in whole meters and we're accepting quite a big error, half a meter. So a possible distribution then would be this. So x is rectangular distributed with values ranging from minus 0.5 to 0.5, remembering that these are the errors. So that would mean that I have this function, 1 divided by b minus a. That's just 1 then. Calculate the probability that the error would be less than 0.1 meter. Okay, less than 0.1, it then must then be between minus 0.1 and plus 0.1. And if I calculate that, I get 0.2. That's the probability that the error will be less than 0.1 meter. Exponential distribution then. Once again, we'll be looking back on the binomial distribution and the Poisson distribution. When we talked about the Poisson distribution, we talked about a number of successes of a certain experiment during a specific time period. If we now instead focus on the distance between the successes, and we let x denote the time from start, or we start measuring until a success, we might be able to get a distribution of x using the Poisson distribution for this. That gives us the number of successes. So let n be the number of successes during the time x minutes. Lambda is the number of successes per minute, m in the main formula, or lambda in the other one. So lambda or m, doesn't matter. It's the rate of success. That's the important thing. Knowing this, we see that n is Poisson distributed lambda times x, where lambda x is the expected value, mean value for n during this period, because if lambda is the number of successes per minute, but I'm talking about x minutes, I have to take lambda times x to get the actual expected value, mean value for this complete period, x minutes, not 1 minute, all minutes, okay? Yes, so the time to the first success exceeds the time x if and only if there were no successes from x equals 0 to x equals x. So what's the probability that we have no successes in this period? Well, using the Poisson distribution with only n equals 0 only gives us this case. And if we evaluate this, it gives us something that is a bit similar to what we had when we talked about the Poisson distribution, but still a bit different. And this is actually the basis for the exponential distribution. And this is the formal definition. So the exponential distribution has the probability density function for a random variable x, looking like this. Depending on where you find this formula, it might be expressed differently. So it could either be like this, 1 divided by a times e to the power minus x divided by a, or lambda times e to the power minus lambda times x. We could either write x is distributed exponential as an exponential distribution with the expected value of a, or like this. But if you want to use the expected value, which is the expected or the average time you will have between when you start and the first event happens, that's the expected value. If you want to use that, you should go for this version. The connection might feel a bit hazy, but anyway, so it has to do with, it's kind of based on the binomial distribution anyway. So we have the following connections. So the binomial distribution models n discrete experiments with a probability of p to succeed. It's a discrete model. The Poisson distribution, when we can also think that the number of trials tends to infinity, and you divide the period you're looking at into really, really small parts and getting the number of successes. And when we do that, we get the Poisson formula. Kind of like the same case, but now, instead of thinking about how many successes we have when we use the exponential distribution, instead we'll be focusing on the time between events. Completely depending on what you want. Is it the number of events in a specific time period, or is it the distance between two events that we're focusing on? These two are discrete. This one is continuous, because time is continuous, but number of successes is of course discrete. I'll just run you through a simple example. So let's assume that the waiting time between arriving mails to a server is described by an exponential distribution with a equals 10. So that means the waiting time can be expected to be 10 seconds, not minutes, 10 seconds on average. We'll define a random variable being distributed t exponential distribution with the expected value of 10. And the probability density function will then be, just going by the formula, this. We then want to calculate the probability that the waiting time will be somewhere between 20 and 30 seconds. I will just be using the definition of probability density function and cumulative density function, where when you want to have the probability for t being between two values, you integrate between those two values, the function that you have. And this might be something that you've forgotten how to find the primitive function to this, but it's not that strange. It's actually this. And you might remember that when you differentiate this one, minus 1 over 10 will pop out. This is the primitive function to this. And once you have this, you just evaluate this formula for first 30 and then take away what you get if you enter 20 instead. And that will be this. So the answer will be 0.0086. Once again, this is not something that you will do too many times, but I think it's a good idea to have seen at least both Poisson and exponential distribution, because they are honestly used a lot. And there are many other distributions that we won't talk about, like Weibull and so on, but this is enough for now. But there is more. So this is the graph of the distribution, and depending on what kind of expected time for something to happen, I mean, if the expected value is bigger, the curve will then be flatter. And that's quite obvious because longer waiting time, flatter curve. So that's not that strange. Ending this lecture on a high note, so normal distribution, which is by far the most used distribution. And so we will be dealing quite a lot with this. So this is definitely the most important one. So why is that? Well, it gives a good description of a variation of many properties. Many things in nature and normal life is normally distributed. The distributions has many mathematically great properties, and it's also sometimes called the Gaussian distribution. And that's because Carl Friedrich Gauss was kind of into this. The actual distribution, the function, the probability mass function is quite complicated. This is the way it looks. We won't be using the formula, basically not at all, but we will be dealing with it in a different way. You will understand in the end. In this, we have two numbers that is not variables but constants. And that's mu, which is the expected value, kind of like the average. And you have the variance, which is sigma squared. Sigma is the standard deviation and sigma squared is the variance. So when you write this down, you write it as x is distributed normally with the expected value of mu and the variance sigma squared. And in this image, you can see how that looks depending on what kind of sigma you have. So if the variance is smaller, you get a tighter curve. And as the variance rises, you get a more flat curve. Why is it flatter? Well, you know, it has to be the area below the curve has to be 1 as always. So mu is called the expected value and will always be in the middle, some kind of symmetry line. And sigma is called the standard deviation. It's the theoretical standard deviation, and it will tell us how much a value will deviate in average from the expected value. You shouldn't mix this up with S, which is based on a sample, although, of course, they are related, because if you try to model a practical sample using the random distribution, normal distribution, they are, of course, related, but that's for later. When we look at an image of the function, we realize that it is, like I said, symmetrical around mu. Also, I don't know if you remember what an inflection point is, but that's a point where the derivative will switch from going up to going down. Here we have an increasing derivative, and somewhere here it starts decreasing again. That's an inflection point. That's not really important, but it's interesting. With mu equals 0 and sigma equals 1, we get the standardized normal distribution, and that has a specific name, which is phi of x, and we will come back to that quite a bit later. Okay, so the Gaussian distribution has the probability mass function for the random variable looking like this, and we write it like this. That was what I said before. And the cumulative distribution function will be this. And you might wonder why haven't you evaluated this into something? Well, the strange part here is you can't find a primitive function for this one, so you can't actually calculate these. You have to use it numerically and do it numerically using probably a computer. And then you will record it and save it in a table of some kind and use it that way. And that makes things sometimes a bit complicated, but you can rest assured we'll fix this in a really simple and usable way. in the end. You might have seen this before though. If you have a normal distribution and you want to know what's the probability that x will be between the expected value minus 1 standard deviation plus 1 standard deviation. You have these numbers. And later on you will probably take this course called 6 sigma, and it is related to this last line where you have a span of 6 sigma, and so you want everything to be within 6 sigma in order to guarantee some kind of quality in some cases. Okay, that might have been a few new things for you, and your head might be spinning a bit now, but I can guarantee we will be back and we will dig into these in a way that you will be able to understand how to use these things and when to use them. Okay, see you later.